Okay, I think most of the people have joined up. Hello again and welcome again to today's webinar when we will be examining how to do camera calibration with 3D survey. With you again is me, Vit Peterman from 3D survey, and I'll be presenting you today this presentation. So first, we will look at, as usual, we will look at some theory on camera calibration. We will be looking at why we need to do it and which are the parameters involved. Then we will do two examples. First one, how to calibrate a drone camera. So for this purpose, I have two drones that I am calibrating. One is DJI Mavic Air 2S, and the second one is DJI Mavic Mini 2. Both of these are new drones, and with 3D Survey 2.14, we will be adding the default camera parameters for these drones. In order to get that parameters, I had to calculate them, and I will show you the tricks involved. Then for the third part of presentation, I will also show you some tricks on how to calibrate handheld camera. So this one is slightly different because it's a smaller one and we can calibrate that one using calibration field. And as usual, at the end, we will have a short Q&A session where you will get the chance to ask any questions you might have. Okay, let's get right into it. So camera parameters, what are they? So let's first look a little bit into the past. So before, the situation was that we had big cameras like this ultra cam in this picture. So photogrammetry was done using big metric cameras. And for these cameras, the traditional workflow was to calibrate them. That meant calculating all the camera parameters, which are focal distance, distortion parameters, principal point location, and these sorts of things. You would do the calibration once, and then you would keep using those parameters for a few months. These parameters would stay fixed, and after a few months, you would repeat calibration, and then from then on, you would use those parameters. This was possible because these cameras were called metric cameras. They were made from special materials that don't contract much. But the situation today is we have simple small cameras like this Phantom camera, for example. So these will be made out of plastic. The parts inside, they will move slightly, they will have stabilization, these kind of things inside of them, which causes the camera parameters to change slightly. Because of that, in this case, the calibration parameters, we have to adjust them slightly every time we do a measurement. So camera parameters with these new simple small cameras, we are only using this as initial values, and for each project that we calculate, we will also calculate a set of parameters that best fits for our camera model. So now let's have a look at which parameters we have for our camera model. So later I will show you how to best access these camera parameters, but we see that we have some parameters here. So we have initial values, so these are the ones that we start with, and then after we do band adjustment, we get optimized version of these parameters. And the parameters are the following. First is the camera shutter type, then F means focal length, PPX and PPY means position of principal point, and then we have a set of distortion parameters. Let's focus first on the shutter type. Just one back. I guess the video is having problems. Yeah, the video is not working. So we will just skip the video. Maybe let's do it. Let's try it like this. Okay, doesn't matter. So the thing about camera shutter type is most cameras have what is called rolling shutter. If you saw our previous webinars, you also already saw this video. So what actually happens is when a camera takes a picture, it's not necessary that the whole picture will be taken in an instant moment. So most cameras that have CMOS sensor inside, and that's most cameras that we have, like cameras in our phones, handheld cameras, most of them, what happens is they read out sensor a line at a time. So first line is read, then second, third, fourth, fifth, sixth. So for example, if you take a picture of a rotating propeller like we have here, you would get this kind of distortion because the different vertical parts of an image were recorded at different times. On the other hand, if we have global shutter, then the whole image is read out in one instant. So when we are setting out camera parameters, it's important to set this thing first. So we need to figure out what kind of camera we have. So now, which cameras have global shutter and which ones have rolling shutter? So turns out from the drones that are on the market now, we have DJI Phantom 4 Pro, DJI Phantom RTK, EB, Inspire 2 with X2S camera. DJI P1 camera also has a global shutter. Then if we have a regular camera with a lens that has a lift shutter, it will also count as a global shutter camera. And then the final part, if the camera is not moving when picture is recorded, then we can also count it as a global shutter camera. So on a drone, to get this effect, you might use stop and go technique. So that means that the drone stops for each picture that it records. But if the pictures are taken in flight, then it's likely we will be using rolling shutter. So rolling shutter, on the other hand, is on most CMOS sensors. So usually it's the lens that turns it into global shutter. If you want to check for your camera what kind of shutter it has, maybe the best thing to do would be to try and Google it. For example, if you Google for camera name, rolling shutter test, you might find this kind of video that will help you to figure out. So in this video, the person is rotating the camera and you see how the columns are dancing. So this is because of rolling shutter effect. This is, for example, Sony Alpha 7S II camera. Then on Sony Alpha 7 III camera, so slightly newer version, this one actually seems like it has a global shutter. So figuring out if a camera has a global or rolling shutter, this is it can be very hard to find this information online. So the best way to do it usually is to find this kind of a test, because even if you ask the person who are selling the cameras, often they don't know about this specialty. If you can't find the test online, you can try repeating this kind of test for yourself. Okay, back to the presentation. That's the shutter type. So this one we need to set up properly. Now the second parameter. So this one is actually the most important parameter of them all. So it's called F, or focal length. So this tells us the distance between our optical center of the camera, so that's the point that all the rays travel to, and our image sensor. So this one is very important because we need a good initial focal length estimate in order to get good reconstruction. And during the calibration process, we will calculate this focal length, so the initial focal length value. So it's important to note that the focal length will change slightly every time we will focus our camera. So every time when you focus, the lens moves or the sensor moves slightly forward or backward until the image is clearest. So this focal distance will also change slightly when that happens. So might be good when recording photos is to always use focusing at infinity. So infinity is usually everything that's 10, 20 meters or further. It's already close enough to infinity for our purposes. Now, what happens when we get bad focal length? So like in my example here, if we have all the ground control points on one level, if the focal length will be off by 10%, then height of objects above our reference plane will also be off by 10%. So in this example, if the focal length was, for example, 3,100 pixels instead of 3,500, then the height of this building would be 10% lower. So that, since the building is 10 meters high, that would mean we would only calculate it to be 9 meters high. So you can see that this one is the most important parameter to have. This is allowed because the other distortion parameters can distort the picture so that everything will still fit together. And because we don't have any ground control points up here, our model might look perfect, but it actually won't be. How to spot a result with bad focal length? So it turns out that if focal length is calculated incorrectly, like in this example that I have here, where I forced bad focal length calculation, you will see that it seems like that the Earth's surface is curved, like looking at the surface of the Earth from a distance, but we know that it should be more or less flat. Also, the camera locations are slightly curved. So if you see that happening, check the focal length, make sure that we have a good value for it. Okay, this was focal length. Now let's also quickly check the other parameters. So the second one is principal point position. So principal point, that's just the center of the image. So the actual center of the image, so that's the focal point. If we project it on the camera sensor, it actually won't be exactly at the center of the image, but it will be slightly off. So these values, the position of principal point, this should be approximately half of the image size, plus minus 10, 20, 30, 40 pixels, something like that. So this is also the case here, where we have 5,400 by 3,000 and something image. Now, the next set of parameters is radial distortion parameters. Now, every image will have a little bit of radial distortion. Actually, the drone cameras, because they are very small and they have very wide lenses, they have usually pretty big radial distortions. Sometimes the images we get are undistorted slightly, so that we don't get these heavily distorted images, but they are already pre-processed. So that happens, for example, with DJI Phantom 4. Pro. So radial distortion will cause this kind of a barreling effect. So a point that on the image is here, it should actually be here. So this point here, it should actually be here if we had the perfect projection. Because we don't, we get that. And during the calibration process, we calculate these values. So these are these three parameters, K1, K2, and K3. And then the final two parameters are tangential distortion parameters. So this causes this kind of effect. A point that should be on the image here will actually be here. So we get this kind of tangential distortion. The key takeaway here is these parameters should be very small, 10 times smaller than radial distortion parameters. And they will be like that most of the time. Well, every time. I don't think I saw an example where this would be calculated wrong because they are always small. And then final parameter, locked parameters. So if we have good initial camera calibration parameters, by default we use this locked checkbox. That means that these parameters won't change during bundle adjustment. They will only change in orientation, either when we have orientation with ground control points or orientation with telemetry. So we found that this actually helps to get best results, and it also makes bundle adjustment faster because less parameters are being calculated during bundle adjustment. But then during the orientation phase, these parameters always get unlocked and we always optimize them slightly. Now let's have a look at practical example on how we do camera calibration on a drone. So first example we'll be looking at will involve Mavic Air 2S. So this is one of the new drones from DJI. And for our calibration flight, we signalized on the ground 9 ground control points. We measured them accurately. And then we recorded multiple images. So for my calibration project, I recorded images from 30 meters altitude and from 50 meters. And I also added some images taken from the side. Let's go to 3D survey. Let's start it up. And I will first load in the images that we recorded with Mavic Air 2. Quickly set up my project. Import. Perfect. So maybe you're aware, maybe you are not. So Mavic Air 2 is missing the waypoint navigation mode. So I had to fly it manually. That means that I had to fly it like that in manual mode and take pictures also manually. So at first I flew at 30 meters altitude, then I rose to 50 meters, and then in the end I also added some images recorded at 60-degree angle. So if the Mavic had waypoint navigation mode, I would probably also add an orbit, a whole orbit, but because it wasn't there, I just added a few of them, and a few are actually enough. So right, now let's check the camera parameters. So because this drone is not in our database yet, here our initial camera parameters are calculated out of the data in the pictures. So in the pictures themselves, we have here, for example, we have here already focal length in millimeters, but you see it says 8 millimeters. This value is not very accurate. So from this value and from additional information inside, we calculated the initial focal length to be approximately 3,400 pixels. Principal point we place by default in the center of the image, and the rest of the parameters we set to 0. And by default, the parameters are already unlocked. Now, the simplest calibration is do first bundle adjustment, by default settings, press OK. So this would take now 2-3 minutes. In order for us not to wait, I will just load a project that has bundle adjustment already complete. And after initial bundle adjustment, we already got improved camera calibration parameters. So some distortion parameters were already calculated. Okay, that's perfect. So this one we need to set to rolling shutter. Okay. And then the next part is do the camera calibration. I mean, do the orientation. Now, during the orientation, we will add this ground control point information. So here on this small area, I signalized 9 ground control points and placed them in a grid. So because we have that many of them, this will allow us to calculate our focal length very accurately. It's just important that these points are measured accurately, that they are stabilized and they don't move during our measurements. So this is general instructions. Now let's do the orientation with GCP Data. Select my calibration select my GCP file, import, next. Identify these ground control points. So here we can actually do it pretty fast. Maybe add this one as well, like that. Okay, we already have all the camera locations identified. Click detect targets. As usual, go through the images, turn off the ones that don't show up properly. More or less it's okay. Just make sure for this kind of things. Okay, let's say that for this example, this will do. And then just press next. And, 3D Survey will make optimization. So we can go ahead and wait for this one because it will only take about a minute or two. So right now, the camera calibration parameters along with camera position and also all the positions of 3D type points are being optimized, and we get this kind of values. So a few centimeters, so that's perfect. Finish. And now our model is geo-referenced. At this point, we would go to camera parameters. We would go here to optimize camera parameters. We would compare them to initial values. And then what we do is we save these parameters into an external file like that. Just put one here, save. And then for future projects, when you would start a new project, when you would do images, load images, you would load in these camera parameters to be used as initial and also add locked here. Now, last but not least, before we use these parameters, I almost forgot this one. It's best if we can check the quality of these camera parameters. And the best way to check the quality of camera parameters is to check the data accuracy. So here I have a point cloud calculated for this area as well. Now, to check the accuracy of this point cloud, I also loaded the data from airborne LiDAR scanning. So here we have some ground points, and we have some points that are classified as buildings. And what we can do now, we can maybe increase the point size slightly. We can zoom in, go to cat, and we can check how well our photogrammetric point cloud data fits to the LiDAR point cloud data. We will be checking delta height. Let's increase the text size slightly to better show on your displays. So then we will just zoom in here by double clicking. We see that LiDAR points are slightly above our photogrammetric points. Now to measure exactly by how much, we'll just go here, use measure tool, delta height, click on the LiDAR point and on the neighboring photogrammetric point. So our point is here is 6 centimeters lower. We can check the same thing on the ground. Like that maybe. Measure the height again. So here this one is 7 centimeters lower. So that means that the height difference remains constant. That means that the height of this building, if we compare the two measurements, both of them seem to be accurate around 1 centimeter. So that means that the camera parameters that we have just calculated are pretty good ones, and we can use these ones in our future projects. Okay, so this was example 1. Now for second example, I want to show you an additional trick. So calibrating a drone camera by doing a self-calibration first. So for this one, for the second project, I did it the same day. I recorded a similar project, but in this one, what I did was I recorded more images. Let's load in the images from DJI Mini 2 drone. Select all of them, open. Read the information from EXIF, set up our coordinate system as usual, import. Okay. So for this second example, I recorded more images. Now, okay, first thing to note, if you plan on using DJI Mavic Mini drone, is this one is missing the camera orientation data. That's why all cameras are pointing towards north. If you get this kind of data, you can easily fix it by going to data, telemetry, INS to camera offset, and we will just rotate all the cameras by -90 degrees. Press confirm, close, go to telemetry view again. Now at least all our cameras are pointing downward. So this will help. Actually, some of the cameras were pointing downward, some I again recorded at an angle, but it doesn't matter. If we at least turn them all down like that, that will already help a little bit. Now, again, our initial camera parameters are not that accurate. Now, because here we have so many images, it turns out usually it helps if you do a pre-calibration on a subset of your data set. So like that, clicking here, I have just deselected all of the images. Now I will use select tool to select only this small part. So 19, maybe let's add a few more. Let's add these as well, like that. 35, okay, I could do it less. We can also use this. So for the first step, I'll set here to rolling shutter camera. Okay. Now I will first do bundle adjustment just on this subset of the images. So this small part should now calculate really fast, again, in about a minute or so. So the image matching is taking the longest because all the images are actually pointing on the same thing. So we are actually matching all the 35 images amongst themselves. And now we will just let this one finish with bundle adjustment. And then we will use the results from this bundle adjustment when we do the bundle adjustment on the whole set of images. Let's just wait a minute more for this to finish. Okay, perfect. Now, this took slightly longer because the initial camera parameters were not that good. Also, because the initial camera parameters were not that good, this warning that we got now, camera parameters might be over optimized because they differ by more than 5% to the initial values. This one, in this case, is irrelevant. So now, so these were the initial values, 2700, and we optimized them at 3000 pixels. So what we will do now, we will save these parameters into an external file, and I'll use like this, for example, 0, 0, to denote that these are just some initial values. So these parameters, and then we will immediately use the open, I mean load camera parameters button, and I will load in these 0, 0 camera parameters like that. So now our initial camera parameters are the same as our optimized camera parameters. That's okay. Then what we would do next, we would select all the images here, press bundle adjustment again, and then do the whole project from here onward. So that means do bundle adjustment and then also the orientation. And after we get the oriented project, at this point, we would again calculate the point cloud, make sure that point cloud is accurate. So here we would use the best way to check that the resulting point cloud is accurate is to either check some point with your total station or GPS measurement, or add some other data, like for example, LiDAR, if you have that available. If the point cloud turns out to be good, go here, save the parameters. You can write here the date. So today is 2021-08-12. Good parameters, like that. And then you would load these parameters on your future projects as initial values. Okay. So this was the second example with some tips and tricks on how to do the calibration. So if anyone will be using either Mavic Air 2S or mini drone, you won't need to do that. These parameters that I've calculated just now will be added to our parameter database, and these will come with the 2.14 update. But of course, because every drone is a little bit different, if you do this calibration for yourself, this will actually help because the lens distortion will be slightly different between different cameras and different drones. So if you repeat this process for yourself, you could expect slightly more stable results. Okay, back to presentation. Now for the third and final practical example, we will be looking at how we can calibrate a handheld camera. So for this third example, I prepared the following. So first of all, what I did was, let's look at the images that I have recorded for the handheld camera calibration project. So these images were recorded with phone camera, actually. In my case, this was Nokia 7 phone. So it's not the best phone there. It doesn't have the best camera. If you try to make a good model with your phone camera, what I would recommend you to do is first, okay, here we will just skip this because we can do this in local coordinate system. So with this phone camera, actually, I find it helps to get good images if you set up your camera slightly. So similarly to as when we record the images with our drone, here as well, it will help if we set a fast exposure time. So for me, 1/60th of a second seems to work fine. It will help if you set a low ISO value, and f-stop, mine is slightly low. It will help if you set it higher because that will give you better depth sharpness. Depth sharpness means that the image will be sharp at different depths. So the top of this statue here will have similar sharpness as this part here that is deeper. Now, I have also prepared a calibration field And just for fun, I have also placed a small statue on the calibration field. And then I went and I took some photos. Now, if you'd like to use the similar process for calibrating your phone camera, I have prepared some files for you so that you don't have to design this calibration field for yourself. So I have prepared a zip file that has inside an A3 and A4 version of calibration field, and I have also prepared a GCP calculator. So let's have a first look at what this GCP calculator looks like. So it's an Excel file. I will just open it. So you can open it in either Excel or LibreOffice. Usually I prefer to use LibreOffice. Then you just print this file, and what you have to do, you need to measure the length of this file. So you would measure, for example, from this point here to this point here, and this would be your length of the calibration field. You would measure to here because it's hard to measure to the center of the point, and you would measure, for example, from here. So from here to here, and that would be the width of your calibration field. You go here, you enter these two values. So I measured it with the measuring tape and I assessed so this is in centimeters, 23.7, and here it was almost 14.2, so I assessed it to be 14.18. So this will calculate the dx and dy distances, and when you input the value here, it will then calculate the coordinates of our ground control points in the field. Undo that. Then what you can do here, you can use this option, save as, and you save it into a CSV format. And I will just name this calibration field 1, for example. Press save. I'll just save this location. Use text CSV. It will help if we set the delimiter as space. This is all okay. Press OK. Go here, for example. We have this CSV file. Added it in Notepad. Then just delete this first part so that we only have the point coordinates inside. Press save. In order to save it, you need to close this one first. Now press save again. Now it will work like that. Okay. The contents of this file I uploaded to Google Drive, and because Google Drive links are pretty long, I shortened it using this tiny URL service. So if you copy this address, https tinyurl.com/ukwvvahp, if you copy this, here, press go, you get to this calibration field zip, which you can download here, like that. Okay, let's go back here. So that's how that's how we get the positions of these ground control points in our field. Now here we have these images imported into 3D survey on top of this calibration field is our statue, just for fun of it, so that we will get something calculated as well. Because this statue is on top of calibration field, it should calculate now, we should now be able to calculate the shape of this statue very accurately. So I taped the calibration field on a box. This is actually a drone box, so that it is flat and that it was easier for me to record the photos. Now the first step would again be bundle adjustment. So here again, the initial values, they are not very accurate. So you see here it's set by default to 4000. Then the first step would be to run the bundle adjustment on these 40 images because the initial values are pretty bad. So the first time probably it will take the bundle adjustment will take slightly longer. What I will do again is just open the project just after the bundle adjustment is already calculated, like that. And we can now check the sparse cloud. So because we are missing any reference point, this is now rotated as is. So then comes the second step, then that's adding the ground control point information. So we go to Orientate with GCP Data, click Browse here. So here is my calibration field that I have pre-prepared. Double click on that one. By default, it will already read it in. So it will read name, easting, northing elevation, and these values that were used to calculate the positions, this will be just ignored by default. So this is all perfect already. Press next here. Now, important thing before we go into that one is to set up the diameter. So then in this phase, you will have to go in here again, take the measuring tape and measure the diameter of this black dot. So if you use my calibration field A4 version, this value should probably print out to about 3.5 millimeters. So I'll go here and I will set this one to 0.35. Go next. Now, as usual, we just have to mark a few ground control points. So I recommend you to select the ones in the corners, first, second, and third, like that. So two of them will be covered by our model. So the ones here, so that's number 9 and number 15. These two won't be visible because our model is covering them. Other than that, you can confirm, maybe improve just this one slightly like that. Use this detect target checkbox, press next. Now all of these ground control points will be detected. So here it will take you some time to go through each one of them, deselect like that the detections that are not perfect, like that. So ground control point 9 is not visible on any photos. Same things should happen to number 15. You would go through all of this, press next, and then like that, orientate your 3D model. So what I will do at this point, I'll just press cancel, and I will just load a project that's already orientated. Like that. And then we get a sparse point cloud that's calibrated with all these points. Because we did it like that, now these optimized camera parameters should be pretty good ones. So they come in the end to 3200 pixels focal length. And here we also have the other parameters. So the T1 and T2 are considerably lower than, for example, the radial distortion parameters. And PPX, so that's principal point X and principal point Y, they are at approximately half of the image size. So this all looks good. The only thing left would be to, for example, make a 3D model of this statue, and then, for example, measure the size of it and compare it, measure the size of it in like the real size and compare it to the virtual measurement, like that with CAD, for example. Like that, let's say measure on the model like that. Just a second. Make it bigger, make the measurement green. Go to measure. Like that, it should be about 6.7 centimeters big. So because, you know, in the beginning we inputted centimeters instead of meters, so everything is actually in centimeters, not meters. So this means that the statue is 6 centimeters wide. And this is how you would calibrate your phone camera. One last thing to note is we set in the beginning the focal length will change depending on how far we are from the model. So in this case, if we record from this distance, the focal value will count for this. If we use the same phone to maybe map a building or something big, you would probably expect this value after bundle adjustment to change by some 10, 20, 30 pixels, something like that. Not much, definitely less than 5%, but this focal distances for when we are mapping something close. When we have bigger things, we can expect it to be slightly different. Okay, so this was now the practical part of this session. Now the final part. Let's see if there are any questions in the questions dialog box. So first one is question from Ales Erker. He's asking, do I need to do calibration for Mavic Air 2 Pro? For Mavic Air 2 Pro, this drone has been around for a while now. So for this one, the parameters are already in 3D Survey. You can do one small calibration project for yourself, place like that, place 9 ground control points on a small area, maybe 50 by 50 or 100 by 100 meters, and do the camera calibration and check the parameters. If they will differ significantly between initial and optimized values, then use your own camera parameters instead of the ones that are already inside. So if they are pretty similar, you can just go ahead and use that one. So probably it will be that the second example. So the camera calibration parameters that you will calculate will probably be similar to the initial ones. So Mateusz Chimielski is asking, can you send us the link with calibration field? Yes, I can. You can also you will also get a recording of this webinar. So actually what I will do now is, if you want to take this link, I will add it as a reply to your question sent to all. So each one of you should now get this link in the question box. Jürgen Jakob is asking iPhone camera for house facades calibration. Yes, yes, I would recommend you to first do a calibration project. So you can do calibration the same way we did it for drones. You can just put some targets onto the, you can put some targets on a facade and then record the images of these targets from various angles in order to get best calibration parameters. Alternatively, you can also use this calibration field. So both of these things will work. So if you do a mapping of a building facade, it might help if you place some of these dots, some of these ground control points on the facade and you measure them with the total station, for example, so that you will be able to georeference your house model. So if you want to do that, you can go to our webpage, sign in, go to the downloads section. There will be here ground control point target 27 centimeters. You can take this 27 centimeter target, maybe scale it 10 times so that it will be only 2.5 centimeters big. Paste it on the facade, measure it with the total station, and then use them as ground control points. By the way, sometime later this week or next week, probably also this calibration field will be added to our downloads section of our webpage. Second question from Ales Erker. One question off topic. What if our GCP points are not rounded but squared chess? Okay, for now, if you have the chess format ground control points, you will need to measure them manually. But I think the support for this GCP design is coming, I think, before the end of this year. So with we are already started adding some support for different ground control point formats. And I think it will be coming with end of the year update. So right now the 2.14 update is almost finished, and I think it will reach you in about maybe a week or two, something like that, after the beta testing is complete. I will wait for a while. I will not tell you yet what the new things are. I will wait for that for a while, but I can already tell you that the end of the year update will also include a lot new stuff about the ground control points. One thing that's coming is the ground control points that are detected automatically, so that means without user input. They have special symbols like QR code, and 3D server will pick them up completely without any user input. Okay. And the final question today, the difference between the LiDAR and drone survey is systematic. I mean, if you fly at 30 meters, it will always be 6 to 7 centimeters or above. So in this example that we had here, the difference was systematic, yes. So when we saw that this area is systematic, then we say, perfect. That probably means just, you know, we use the GPS to measure this point. The LiDAR used its own GPS. We expect there to be some systematic difference between the two, maybe a few 5 centimeters, something like that. Turn on the ground and building layers. Increase the point size so that we can see them. Because the difference is systematic, we know probably, okay, either our GPS or their GPS showed a slightly different value. Also, this LiDAR data is now already maybe 7 years old. So back then, maybe they applied another GeoIT model because, of course, it was updated. And when they update it, it changes by a little bit. But what we are checking with LiDAR is if we get the same shape. So relative accuracy of LiDAR will be very high. So if you measure a height of a building with LiDAR or with measuring tape, you would expect to get the same thing. So this is what we were checking here. So I checked if we get the same error up here and down here, and that means that because we would expect there to be some systematic error, that everything is perfect. So it won't be always 6 to 7 centimeters. So this LiDAR is available for our whole country. And on some parts, it may be 12 centimeters. There may be 8 centimeters somewhere else, and somewhere else, it may be just a few centimeters like that. So, okay, these were all the questions that we had. So at this point, I would like to thank all of you participants for participating at this webinar. So as usual, everyone will also get a link with the recording for this webinar in order to check it out at a later time if you need to check something. So this will be it. Thanks again for joining. Bye-bye and see you in our next one.